world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons.
Up later.
All right. Hello and welcome, lads and ladettes. This is Celestial Theodolite update number 34. Got a couple of things to go over this week. We're going to touch up on astronomical refraction and an astronomical refraction update to the spreadsheet and layout changes. And then we got some new data from the 24th and the 25th. The new data has not been parsed yet, but we'll go over a couple of the videos and stuff just for funsies, and then we'll do Q&A and wrap up for the night. So to start us off here, let's see, a couple of, I think it was 2 weeks ago now, because we took last week off, we discussed how we would be going over astronomical refraction. So in the explanatory supplement to the Nautical Almanac and the Ephemeris and the American Almanac, etc., the British Crown put out this, explanatory supplement to how they came up with the equations and everything and the corrections and whatnot for the Almanac and for the Ephemeris, etc., and how they do that every year. And so one of the references they talk about, like obviously the book is based on the geocentric position of the star, which is, we call it, the true position. We often refer to it as that, which is what defines the 60 nautical mile, 15 degree per hour positions of the star, and for the purposes of using celestial navigation or the graticule or anything like that. So basically, the backbone of what everything comes from. And then they have a note here about the refraction position. So they talk about how to deal with refraction in practical use. So there's a couple citations here given from Smart for spherical astronomy, and then Chavent, who has a manual on spherical and practical astronomy, and they talk about how you do a site. Oh, I'm not screen sharing in my Shane. Thank you, sir.
Okay.
All right. I didn't even have to read it. I saw the thing pop up and I was like, oh, okay. I know what the issue is. It's me. It's me, guys. Okay. So anyway, the purposes of how to deal with it in terms of like reducing it so that you can get the geocentric position of the star relative to your position, so you can define its ground position, so you could begin making your circle of equal altitude. They talk about how, basically you use these formulas with your local temperature and pressure, and these formulas based on the elevation band that you're looking at in terms of like 10 degrees, 20 degrees, 30 degrees within those bands, etc. there's an output for how much refraction there should be, and then you just subtract that out. So part of the process of sighting a star and all that is reducing out that refraction amount. So how to do that is in there. And then the theoretical discussion on the calculations of refraction are included here. So there's some manuals here on how they came up with those formulas that these lads are using, because the output of the formula is just some coefficients. You enter your local temperature and pressure and the angle that you're observing, and then the output is exactly how much refraction there needs to be to explain what the angular difference between the star's position is when it's moving at 15 degrees per hour and 60 nautical miles per degree versus the apparent position that you see. As things get lower in the horizon, the difference between the two gets greater. So they need basically, a mechanism to explain the difference, and they go with refraction, obviously. So in the backbone of how these how they come up with these models, basically the models start off with boundary and input conditions set to Earth's radius, and then from there they build a stratified concentric sphere model, which ends up producing something like this. So you see XECA here. All of these you can consider, like, the distance wise, it's not to scale or anything, but the way they layer it out, these are infinitesimal concentric shells that surround Earth to make their gradient. And then this is what we're looking at as a light beam, travels through that. This is how it's going to bend and curve gradually to fit that model. So after all the math is said and done for laying out the structure of the model. By the time it gets to the point where you can put in your real local data, the data gets smoothed out into the model, so there's no anomalies or anything, and it fits to what the quote unquote globe would perfectly predict. But the problem with this model, or both of these models, because let's see, there was 3 references given. The one guy I couldn't find, it's in German as well, but the 2 English ones, they all suffer from the same problem. They're creating like a static model. They're not dynamic models. All the conditions that would be like, thermal inversions, ducting, any sort of turbulence in the wind, none of that is in their mathematical model. It's exactly concentric circles that provide like the exact mechanism of how much it needs to fit all data into the model, so that you can put anything like real world measurements into it, and the output will be what the quote unquote globe predicts. So going through all of that, and one of the most important things that I read from here was that this gentleman Willis was talking about how they get the air density for their calculations, and that's a important factor, the assumption of how much air density there is to distribute that over the atmosphere so that they can describe the bending of the light. They use circumpolar star observations. They just observe the stars, and then they guess at how much air density there would have to be to produce the effect that they're looking at, and then they take that and use that as their primary way to describe how much air density there is. And this guy was saying like, hey, we actually now have the technology to make these precise measurements of this level of air density in the lab, and we never do it, and that's a real shame. And he would like to see more actual measurements to confirm the calculations and stuff that they're doing. So both of these papers do the exact same thing in terms of constructing a model, and then it's made such that any data integrated into the model will be smoothed out and distributed basically homogeneously throughout the model. Okay, and to kind of test that, theory, we took measurements at Getaway Peak in July last year, and then on December 31st, we went back to the same spot and took measurements again, which we went over a couple of weeks ago when I first presented those. But in that, I did not change the actual temperature in Stellarium to get their refraction update amount. And I realized that we hadn't really done that for any of them. We left them on the default, which is 15 degrees Celsius. And so I went back through, got the temperature data for all those locations, and went back through and went to, saw how Stellarium would change those numbers. And it didn't really change anything too much. Like we're talking between like 40 arc seconds to 1 arc minute of difference and change between those. And I thought that was really interesting too, because especially in a 6 months time span where it's at a completely different time of year, the refraction value only changed by 1 arc minute for Getaway Peak for one of the stars. And to be 1 arc minute off, because they say that, stars at the horizon and refraction at the horizon's questionable, they don't have a good way to predict it, etc. Well, being 1 arc minute off is pretty decent in terms of just looking at raw observation to get your location using a circle of equal altitude. That would only put you off by 1 nautical mile, so it's not so bad in terms of how it affects it or whatever. So it turned out to be like pretty negligible. So the difference between, and some of the temperature swings were like 20 degrees or so in terms of temperature, and it didn't really change it that much. So but we will go over the changed values, and I also changed the layout of the spreadsheet to make it more readable, and we'll go over those changes now. So the primary things that I added some in-house notes. So you can, when you mouse over these, you'll see notes now. So that'll kind of help tell you what things are. And I'm going to go through and add more of these, so it'll be more easily available. That way you don't have to reference the notation.
It's pretty dope, actually. Nice.
Yeah, you don't have to go through and reference the notation guide, which is over here on the Obsidian page. You can keep it all in the same thing. But of note here, I added to this section. I'll link the spreadsheet here in the chat too, in case anyone wants that link. So a couple of things I added. I removed the. We're in the middle of a presentation right now. Good, sir.
How you
So
doing?
yeah, we're just gonna go ahead and he left. All right. Okay, so we have this here is now in bold, this intersection point for flat Earth and for globe Earth. This is now has little boxes around it because this is the key important part, so to speak, because the differences here are what create the differences in elevation when we go to derive what a triangle would look like if we use the occlusion angle versus what's predicted for both models, like position wise. So if we use the star's true position at the peak, like it's off by a little bit. And when we do it for the globe lads and we do the triangle from the position of where the occlusion happened for the observer with the star's true position, that they're off a little bit too, and they share an error. Well, that shared error, the sum of that is the half gamma, which is the expected drop over distance of that particular distance. So anyway, I just highlighted this to make it, the more relevant part so that you can see where the differences come from and whatnot. And I moved the perfect idealized globe and the central angle stuff all down here so that it's not confusing. I kept seeing a couple of times, well, actually more than a couple of times, but people would look at the perfect globe stuff and go, well, what's wrong with it? The globe predicted, not understanding that this is like a math check to make sure that we're deriving things correctly. And there's no occlusion here. This is all based off of just what the peak and distance wise represent to calculating on a globe. So this is so anyway, I moved this to all down here so it's out of the way. Some of the math check stuff that was over here and underneath this and looked all messy and all that is now under here, and it's properly labeled. And I'm building a section for the which I'll add up here as well to the total summary, because I know the lads like to see the apparent position of the mountain peak. They want that to be included as well. And we'll be able to see more easily the differences in geometric position of the star relative to the refracted peak and to the unrefracted peak as well. So that'll make it more easy to understand. And there's some notation here in these boxes, or I'm sorry, notes here. So negative, sometimes these will be negative, sometimes they'll be positive. We now can easily distinguish what those mean. So negative means the apparent position is above the peak. Positive means it's below the peak. And for the geometric position where it's in pink, the negative equals the true star is above the peak, or star's true position, and positive equals the star's true position is under the peak. So the only difference here is just the word apparent and true, but the metric of positive and negative remains the same. So all those are now consistent. And let's see, work in progress stuff. Move some of the approximation formulas down here in case anyone wants a approximation formula, but just kind of cleaned it up a little bit to make it more readable. So globe stuff here, or flat Earth stuff here, globe stuff here. Refraction analysis for the globe lad stuff is now more up in the forefront to be able to read.
A link.
What's that?
A link to the spreadsheet for people.
Of course. Link in the chat for Celestial Theodolite. And then we've got...
It's a way that they can't edit it or anything like that. Or they can edit it, make a copy.
Yeah, so because of the drop-down menu situation here, you're not going to be able to come to the sheet and use it yourself. You'll have to download you have to make a copy on your own thing, and then you can edit it and all that. Let's see here. So let's go over the data points real quick. So for Pike's Peak, with the new refraction update, they barely moved it. Instead of being like 12.48 or whatever it was, it's now 13.23. But anyway, that makes it a little closer to the apparent position where they predict 219 by adding 2 arc minutes of refraction. But for the geometric intersection, of course, they're still over the peak by 2 arc minutes, which would not lead to an occlusion. Or no, I'm sorry. Yeah, that is the refracted. So yeah, they're still over the peak on that one. So Blodgett, we'll just run through these real quick. Let's see. So for Blodgett, still above the peak, this time by almost 3 arc minutes, which is pretty crazy. And then for the apparent intersection here, I have apparent peak and then the delta apparent star to peak, which is the difference between the apparent peak and the apparent star position. So now they're at they're negative here. So the star is still above the peak by 1 arc minute, 23 arc seconds at the time of occlusion. Like even if you were to consider the apparent position as the occlusion or whatever, this doesn't lead to an occlusion. It means it's still above it. Let's see. Cheyenne here, we got for apparent position to geometric, they're above the star, they're above the peak by 2 arc minutes. So again, not leading to an actual occlusion. And here we have for their refracted peak, this actually brings them closer to what they would predict for the apparent on apparent intersection here, which, I reject that premise. We've been over that, but the numbers are here nonetheless for your viewing pleasure. So this brings them down to 30 arc seconds in closeness. Now, if these numbers were like more consistent across the measurements, where it's like, okay, we're lining up in the arc second range every time, it would be a more tenable position that, that predicting the occlusion off of the apparent position would make more sense. But as we're going to see here, these are going to fluctuate to mismatch and not lead to any sort of occlusion as we continue here. So let's see. So here they're slightly above the peak, but only in the low arc second range. Well, half of an arc second rather, or half of an arc minute rather, which comes out to be 3 seconds, but it's pretty small difference there. And then for the geometric intersection, they're still 2 off for the apparent position with respect to the geometric peak, which is 2 arc minutes off there. Then as we continue on, we have Blue Mountain coming in at 19 arc minutes of refraction this time. This one ended up also putting them a little closer to what they predict for the apparent intersection there. And we have 2 arc minutes of being geometrically above the actual peak, the physical peak. We have, let's see, Mount Rosa. Mount Rosa comes in at 24 arc seconds, so again, pretty close on the apparent there. But then 2 arc minutes above with the light source, essentially. So, or we're with respect to the physical peak. So still 2 arc minutes above Green Mountain. And Green Mountain, they are, 2 arc minutes above the predicted refracted peak. And then they're also 4 arc minutes above the geometric peak that they predict. So it ended up this would not lead to an occlusion. This would mean that there would be 28 more seconds before the star actually gets occluded there. All right, and then we have.
Is there any ones that match the globe?
In terms of like geometric intersections, 0.
Geometric intersections.
No,
okay.
never. Let's see, North Peak. Now, North Peak is a crazy one because this was the longest distance that has been done. And let's see, comes out to be, so they end up being 2 arc minutes above, or no, below the peak, sorry. They end up not being able to compensate for it. So in terms of refraction compensation, they undercompensated by 69%, which puts them at 2 arc minutes below the peak. So they predict that would have already occluded 30 seconds ago. And then for the apparent intersection to the geometric peak, there are 3 arc minutes over, which means that it wouldn't have occluded until another 40 seconds for that intersection to occur. And then in terms of geometric to geometric, they're off by 5 minutes. Flat Earth is off by 3 minutes there. And then this section here is real world time, not angular units here. And this goes to what we're saying about how the stars are not following the 60 nautical mile per degree drop for the true position, because if they were, when these intersections occurred, they would have to occur at these later times to match these angles. But the thing that it matches is the distance traversed from the observer. So like all the arc lengths of all these, when we do our arc length check in star drop, they always come out to be basically the way what it implies is that the star was able to angularly drop relative to that observer until it intersected that peak at that distance. So it kind of binds it together.
Can-
Go
Could you
ahead.
do
Keep that right.
houndstooth? Could you do
Yes.
houndstooth?
Well,
Yeah.
Sure. Well, we'll get to it.
I was
It's,
saying before
down there.
houndstooth, brother.
Mhm.
On the top right, where it says actual occlusion,
Mhm.
FE predicted time, GE predicted time, and GE predicted time again.
Mhm.
Is GE predicted time on the very bottom?
Mhm.
That is that the
That's the
apparent? Is that the
Yeah, that's the apparent position to geometric peak. So it'll be the apparent position with respect to this prediction right here.
that prediction right there? Okay, so when it says actual occlusion time, 21:08:21,
Mhm.
FE predicted and GE predicted versus GE predicted apparent.
Mhm.
Oh, I see what you're saying there. Okay. So I'm just trying to figure out where are you getting the difference? Like, oh, this is off by this much, that's off by that much. Okay.
Yeah, just the angular
So
difference between those positions converted into time for drop relative to the peak.
so 3 minutes and 17 seconds is how far off the actual occlusion to the FE predicted time was, and then same thing with the GE predicted time in terms of the true angle, 5 minutes and 7 seconds off of
Yeah.
that of. Is
Yep.
that what that means? Okay.
Yeah. So if the star were still following the like dropping at that 60 nautical mile per degree rate, then the intersection would occur, at this later time, but it occurred exactly when the star traversed the arc length. So this 130 kilometer distance converted into an angle, I think it comes out to be 1 degree 10 arc minutes. So as the star's true position dropped 1 degree 10 arc minutes in the sky, it was immediately occluded by a mountain peak at the other end of that arc length, because that's the only thing that's at the other end of that relative to the observer. And the globe already missed their window for it. They would never get the full arc length out because they predict an earlier occlusion. So there would be a difference in the arc length drop relative to the observer, and that's never the case.
Gotcha. So
Actually,
you're basically saying
yeah.
the arc length from the observer to the mountain peak, that's the arc length,
Yes.
right?
Yes.
And then the globe essentially should have had an occlusion earlier, because if it's just the stars going behind the mountain peak in terms of it's just declining at a fixed rate, aka
Would have already happened for the
Earth
observer.
rotating.
Mhm.
Right. I gotcha. Okay. Just want to make sure I understand that again.
Nope, you got it. And then let's see here. There was something else I wanted to touch on. I can't remember now. We will continue. But yeah, that's the basic premise of that. And then I'll notate this a little better so it's easier to understand, because it just says globe predicted. There should be like an apparent symbol. I tried to color code it and just make it, obvious or whatever, but
No, it's obvious.
well, some people were having some confusion with it.
Well,
so
we've
we'll
seen
move-
your highlighting, so I don't know about
How-
color coding as well.
How
I didn't want to
double
say
dog-
anything.
How double dog dare you? All right, so for getaway peak here, we have, let's see, with respect to the apparent positions, right, they ended up being above the peak by 2 arc minutes here. And then for the apparent peak, they're actually a little closer on that one now. So they're at 13 arc minutes for the apparent, to the apparent. Which, doesn't cause an occlusion, in my opinion, as we've shown, but nonetheless, it is included. So houndstooth here. For houndstooth here, we have a geometric intersection miss by 1 arc minute. So we got a positive here, so it predicts that it's below the peak already. So it would have occluded 7 seconds for the apparent, and then for apparent to apparent, there's 1 minute and 33 arc minutes above the peak, or I'm sorry, 1 arc minute, 33 arc seconds above the peak. So still no, this wouldn't lead to this was an emergence rather. So they predict that it would have already emerged by that time. So who was asking about houndstooth? Did you have a specific question?
No, that's great. Thank you. And could you do gateway real quick too?
Mm-hmm.
Thank you.
Back to getaway. So getaway right here. 2 arc minutes off on the apparent to geometric intersection and 13 arc seconds on the apparent to apparent.
Oh, I'm so sorry. Can you do gateway? I said the wrong way.
Gateway. This is
You mean getaway?
getaway. Yeah, there's
Oh,
only
is it
getaway.
getaway? Sorry,
Yeah.
my bad.
Yeah, you're good.
It's all
Thank
good.
you. That's what I wanted. Thank
Oh,
you.
no worries. All right, and then we have we did Houndstooth already. We'll go to Old Blenny. Old Blinsky. Okay, so this was an emergence as well. So this will be the star's ability to overcome the peak at that time, or at the time of emergence. So for this one, we have it is below the peak at that time by 2 arc minutes, and actually because it's an emergence, this needs flip flopped, so it would be above the peak at this time because 130 is higher than what this is. So for an emergence, you have to flip this. So they would they predict that they're already above the peak by 2 arc minutes, but it didn't emerge until it was at that same angular drop there. So still
Shouldn't it
aligning.
emerge even
Alan,
earlier?
can I just maybe ask a quick clarifying question because I might have missed something. The emergence, is this like an opposite of occlusion?
Yes. This is looking east,
Oh,
and you're looking
no,
at
we're
you're looking at the star coming over the
okay.
peak.
I just want to make sure I understood what you were talking about because I missed some of the beginning there. I just wanted to make sure I was correct. Thank you.
Yep, no worries. All right, so yeah, they
Yeah, I was going to
predicted.
say about the emergence. Shouldn't it be earlier too? If
Yes,
things are refracted up,
yes.
like
So
in the conception. Oh, sorry, go ahead.
no, yeah, exactly. So like I said, for the emergences, you have to flip the meaning because it's opposite. So if it's negative, it's going to be already above the peak. So it's already above it by 2 arc minutes at this time, and that's not what happened. So so using the apparent for that is not tenable. And then for the apparent to apparent, it would have already been over by 1 arc minute, which is 7 real seconds. So it should have emerged earlier than it did if that was a tenable position. But again, the only relationship that's holding is the star's angular drop relative to the observer in terms of like time it takes to traverse that arc length, but the angles aren't lining up. And the only reason that the time would line up and not the angle is if the star's true position isn't following the 60 nautical mile per degree relative to the observer at these angles. It starts to linger, and there's no way to describe, like there's no mechanism for the true position to be lingering like that in the globe model. And I'll put up a little
Just has to refract.
well, it's the true, so it can't. So so here's a little graph that Brian made showing the celestial sphere at these angles. So like the occlusion should more line up with these. Like I was saying earlier, like the reason that these timings are off, but the occlusion still occurred, is because the star's true position, the light source, intersected with the peak relative to the observer, but not at the angle course, in slash time predicted by either of us. And that would only be the case if the star's true position wasn't following this blue line. And as you can see here, it is not. All right, and then I'll put this in the chat as well for any curious lads. Oops, that's
Oh, the blue line represents the celestial sphere.
Yeah, this is 60 nautical miles per degree all the way down to making a full ball, and it doesn't.
Those are the occlusion time. The star geo angle is the actual occlusion time.
Yes, star's true position at the time of occlusion.
Got it.
Yeah. Okay. Oops. And then let's see. We got another Blinsky here.
Literally, it looks like if you were to keep that graph going, that it would make like opposite trends.
Yeah. So Blinn here showing the same relationship would have already been over by 1 arc minute. It is closer on the apparent to apparent, but tomato potato, it still would have been over. And
that's an
like
emergence
the other
again.
one. Yeah. And then for the other star, because it's kind of like an uneven lopsided hill or whatever, so each one has its own kind of elevation, so we're getting a range of how the refraction condition is aligning up with the elevation difference. So here it ends up being almost 3 arc minutes above the peak at the time of emergence. So it would have emerged 17 real seconds earlier, and then refracted to refracted, it would have been 1 arc minute before, so it would have emerged 7 seconds earlier. So none of these, the occlusion time, or the emergence time rather, is the time in reality to which we compare the model to. There was actually recently a lad in Discord who was consistently maintaining the position that why is the occlusion necessary? Can't we just simulate everything in Stellarium? And the answer to that is no, because you're not comparing the model to anything. You're just comparing the model to the model, which doesn't make any sense. We have the real world occlusion because we have to have something in reality to compare the model to. So that's if anyone kind of had a question about that or was thinking that, that's the answer. It's absolutely
That's the
necessary.
equivalent of we investigated ourselves and found no wrongdoing.
Yeah, it's identical to that. And then of course we have Goose's measurement of Varley SE2 and Regulus setting in. So for this one, it ended up cleaning up the globe a little bit. They're only 38 arc seconds off of their intersection here, which is 4 real seconds. But that's a pretty close timing though, so like I'm not mad at them or whatever. And then for geometric intersections, they ended up being hella close here too. So down to 1 arc minute, that's pretty significantly close. So for apparent to geometric here, they ended up a lot closer than what they normally predict. And then of course for geometric intersections, they're still off on that. And then we have...
So what is your model for the motion of these celestial objects?
They go in a circle around us, following pi and over periodicity.
But if the surface were flat and you view a circle from an angle, it doesn't look like a circle anymore, does it? It looks like an ellipsoid, doesn't it?
Let's see here. Let's see. 1 second. I got you. So our premise is that the stars move in a circle above us and we see in a sphere of vision, right? So in this, we have the old... So 1 second, let me lay this out for you and it'll answer your question most likely. So we have the observer here. He sees the stars and everything in his dome of vision, observer centric. And then
you're trying to get me to
Tony, I'm not going to be talked over at my own thing. You're mistaken if you think that that's ever going to happen here. No, I'll just straight mute you, dog. So listen, this is what the observer sees on a flat earth. And this is what a globe lad sees. They both have to use a sphere of vision to get an azimuth to a star. So how we see the stars and how they move, we're just taking the old celestial sphere model. The Chinese also used the celestial sphere model in the 1400s on their expeditions in the Antarctic, and they plotted out the star canopus and all of that. So same exact model, same exact thing. They were geocentric flat earthers using the same star position relationship. That's it. So in this model, we're granting that, both of us see the hemisphere of vision, but that's how we're defining azimuths and positions to stars. And we're granting the 15 degrees per hour, and we're granting the 60 nautical mile per degree relationship, and we're testing that to see if that's true. Because the only difference between how we perceive these stars is going to be the star's true position. But nobody sees the true position, right? There's never really been a way to test the true position. And through the occlusions, that's what we're testing. And we're seeing that relationship of how we see the star versus where it isn't what the globe is predicting. Now I'm going to go ahead and unmute you so you can ask your follow-up questions. Thank you for listening patiently. Go ahead.
There was no point to any of what you just said because I cannot see your presentation. Your presentation is a flickering green screen.
All right. I'm gonna go ahead and mute you. That's unfortunate that you can't see it or participate.
Can anyone else see it? Is everyone else good? I'm good on my end.
I see it perfectly fine. Maybe his computer on his isn't working or something like that. It looks perfectly fine. I see
You can
the
look on YouTube, Tony, as well. It's being multi-streamed or multicasted on different platforms.
Here's a screenshot. Oops. Here's a screenshot posted in the chat so you can see it. But we all use the same conceptual sphere for the modeling. We all see the stars. There's not a special different way that we see them just because the Earth's flat. We're saying that we see them in this dome of vision. Go ahead.
If you say that if you pick up a coin, for instance, and it looks circular when you look at it straight on, but if you tilt it towards you, it stops looking like a circle. If you are on a flat plane looking up at a circle from an angle, if you are not under the center of that circle, it is going to look like a tilted coin. It is not going to remain circular.
We see in a sphere of vision, the stars arc across the horizon due to our vision.
That is not an explanation of what I just said. You
Listen,
just saying
listen, guy.
There's a sphere of vision does not explain away geometry.
Both models use the same sphere of vision.
Yes, but
what, dude? If we see it the same, then it's the same. We're granting the premise and testing the model. If you don't grant the premise, that's a completely different conversation.
You're not listening to him. Listen to him.
Yes,
He's right.
I am.
No, Tony, you're right. He's not listening to you.
Jeez.
So if you are claiming a geometry for the system, I am pointing out that in your assumed geometry, if the Earth were planar, we would not see a circular path. You saying, well, we see circular paths, that's my point. My point is that the fact that we see circular paths is a disproof of your assumed plane. If we were flat and you were looking at the circle from an angle, it would cease to look circular. If you look at, for instance, you'll often see disc lights in ceilings. If you are directly underneath the light, yes, it's circular, but if you move off to the side, it stops looking like a circle and looks like an ellipse.
We're not looking at discs in the sky or what have you. We see in a dome of vision, and as the stars move across, the reason that they change position is due to our vision. You guys say that it's due to the dude. We're not talking about a physical object, bro. We're looking at stars. We have completely different cosmologies on that. It's just a little dot. It's a little dot of light.
What about
How do you know that stars aren't physical?
Oh, just to, I mean,
dude,
my understanding is that Alan is still in like the initial like presentation part of the event. So I don't know. This isn't necessarily like open debates, like part of it, right?
But this is my point. He's supposed to have a model of when these celestial objects are coming into vision and when they're not. So he has to have a model, and he is trying to claim that his model for this is more accurate than the spherical Earth model for this. In order to do that, he has to have a model for the motion of celestial objects that can be interrogated. He isn't presenting it.
And Tony, I was actually backing you up. And Shane, what I was asking you to do is just listen to what he's saying, because he's talking about an object. Now, if the lights are not round, they're not spheres, then fine. But what about things like the moon, which you can actually see that are circular? And to his point, they aren't going oval at the corners. Like if it was a celestial sphere, they would be ovaled at the corners and not still round. That's what he's saying. Does that make sense? Shane?
If you assume that the sun and moon are 3D physical objects that you can go to, etc., then yeah, that would probably be applicable. But we don't, that's not our cosmology. What we're saying is that we see, do not interrupt me, bro. In the middle of me speaking, you're just going to have to put you on mute for a minute here. So let me lay this out for you, okay? We're saying that we see in a sphere of vision, there's a ton of evidence that shows that vision is not Euclidean, okay? Just saying we observe the stars, therefore globe, is retarded. Now, what I'm showing you in that picture is that the globe, quote unquote, the backbone of it, is using a a literal limit, a hemisphere of vision. Okay. Now on a flat Earth, we have, guess what? Our eyes are the same. We don't have different eyes because the Earth's flat. How we perceive the celestial bodies move in the sky is based on our vision. That's it. So this concept of how a star changes in position relative to an observer is based on a sphere of vision, how you perceive it, how it changes angularly. So we're testing that. The globe says that they will move at 15 degrees per hour, 60 nautical miles per degree with their true positions. That's what the globe claims. We claim that they're, above us at all times and they're not truly going beneath our feet. So we can test this claim that the globe is making through occlusions. Because if it's observer centric and the Earth is rotating, changing the elevation of the position of the stars, that's going to cause them to occlude earlier, regardless of either model, right? That would be a geometric fact that occurs because of the shape of the Earth. Now, that occlusion time never happens. What does happen, however, is relative to the observer, the time it takes for the star to move angularly over that arc length, it all of a sudden gets occluded before what's predicted using the 60 nautical mile per degree relationship in every single case. So the model we're testing, that you're claiming that we have to have something to test and yada, 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 we're testing the globe right now. If you want to test a different model or something, that's a different hypothesis, dude. We're granting the celestial sphere model. We're just saying that the change is due to our vision, not the shape of the Earth. And we're saying timing wise, 15 degrees per hour, the positions in the sky seem to follow that pretty good. So we're granting that as well. And we grant the 60 nautical miles per degree for testing purposes. Okay. So we don't have a different system or whatever, right? All we have is what the stars are doing that's observed. And that's what the entire models are based upon. Somebody took a Zenith measurement of a star once and added 15 degrees per hour to it and constructed the whole model. That's it. So you have it in your head that there has to be a different thing. We see them shape into ellipses and whatnot. Bro, they're little point sources of light. They're little dots. How they move in the sky is a facet of our vision and or the shape of the Earth, assuming parallel light rays and all that. So we're testing that to see which is true. Now I'm going to continue on with this presentation. We'll do open back and forth later. But the point you're getting hung up on is irrelevant. Okay. And we're almost done here. So Goose's measurement ended up being closer for the apparent to apparent, and it ended up being a little closer for the apparent to geometric there, but geometric to geometric, still off. Now on the more recent one that we did, following up on the Getaway Peak, this is right next to Getaway Peak. It's about, forget the azimuth difference, but it's like 20 or 15 degrees or so away from yeah, it's called Pueti Tempe Kukakatitaki. I don't know, but anyway, this one ended up being 23 arc minutes off of the apparent to geometric there, and then geometric to geometric off by 23 arc minutes, 12 arc minutes for flat Earth, and it ended up being 2 arc minutes above. Let's see, it was positive. So geometric to, or I'm sorry, apparent to apparent, it ends up being below the peak by 2 arc minutes. So mismatch there on all of the predictions, except for the fact that the arc length traversed relative to the observer. That's when the occlusion occurred. So let's see. Next part. Now, the new data that we have, we'll go over. So we got some new occlusions. Now they haven't been added to the sheet yet or anything like that, but I went through and got timestamps for everything so far for the ones that have potential to be added. So we usually look for stars that have multiple stars on screen so we can identify them by their pattern or whatever. So anyway, some new occlusions there. Scroll through some of these. The nice bright one there. All right, yeah, we got about 18 last night, or 2 nights ago, and then last night we went out and got some more, which I'll show you guys now.
Nice.
So for this one, because we were wanting to test how that celestial sphere deviation at higher angles, we got nice, and I think we're probably about a mile, maybe sub 1 mile away from this peak, and let's see, no. Oh, I haven't transferred them yet. Give me 1 second. We can talk about something else now, or real quick if there's any questions. I'm gonna pause real quick while I turn the C star on, and I'll put those on so we can see them real quick. All right. All right, while that's booting up, I will pull up the history of vision here. Could take a look at that. Where was that?
Powering on, ready to connect.
I don't know, Alan, if you don't mind. I don't know if you've done a presentation or not on the actual or not celestial, I can't remember the first word. The dome of vision, the azimuthal dome of vision, I think it's called.
Mm-hmm.
Like, could we maybe get a presentation on that in and of itself?
Sure. Shane's done quite a few of them already.
Okay. Okay. Maybe I'll look it up. No problem. Thank you, Alan.
Yep.
Shane's about to spam you, Rob. Don't trip.
Okay. Thanks, Shane. I appreciate it. I'm driving right now. I can't look at it yet, but I will.
Shane's like, crap, I gotta pause my game. Thanks a lot, Beast.
Yeah, I'm just waiting for someone to address the math and none of the peripheral nonsense where they just try to be fallacious and sophistry about it. Like, someone go through Pikes Peak and show us where we're wrong. That would be a valid refutation. 34 weeks and no one's done it. I'd like to see it. Maybe Tony's the guy.
All right, so this comes out to be about just an estimate. I think it's like 10. It's over 10 degrees off of the horizon. But here's some of the pictures and videos from last night. Oops, yeah, here's a really cool one. Every star in the northern hemisphere set into this, I guess. Yeah, this was a really cool one. That's the most stars I've ever seen in one frame while looking at the horizon-ish.
And what mountain peak are you looking at?
Ooh, unclear at this time. We have not ID'd it yet.
Okay. I thought you were gonna say the other one.
No,
Takaniki, or whatever it's called.
We were driving home and I was like, oh, we could just pull over right here and use this peak because it's like, super close and the angle, because we were really close to it. So anyway, we went and got a bunch of measurements from here at different locations on it. So anyway, this will all be hopefully added by next week. We'll get all that in the spreadsheet, get it integrated in there. All right. So regarding spherical vision and whatnot, there's a whole history of that. I linked a screenshot, the kind of a meme that I made that has a bunch of references in it, but one primary one that I would recommend to anyone interested in the conversation of how vision works. Let's see. You've been upgraded to Zotero 8. Nice. God bless. Let's see. Where's my Wagner? Of course. That's not how you spell Wagner. The geometry is a visual space. So in the first 3 chapters here, this guy goes over the histories of all the primary theories that were put forward to describe optics and how we see the differences from the spatial field and the visual field, and how those theories failed, etc.
Nice. Good old Wagner.
Yeah, but basically, right, we all let's see, oops, let's run this one. So that's what we're testing there, right? Is the globe model work because the Earth is a globe, or do the stars change positions because of an optical phenomenon? If the Earth is a globe, then these occlusion intersections would be mismatched. They would be reversed. So instead of flat Earth being 11 arc minutes off, instead of flat Earth being 2 arc minutes off, it would be 11 arc minutes, and globe Earth would only be 2 arc minutes off. But none of that ever happens. So, and then of course we have the apparent positions with respect to the geometric and apparent to apparent, and we see that we end up with scenarios where the star will either be below the peak at the time or should have already been above it, and it doesn't actually occlude until the arc length difference relative to the observer is traversed. So, which indicates that they're not following the 60 nautical mile per degree relationship at these angles. All right, and we've been over the refraction differences at, let's see, where did I add that?
Surprised you have like no questions yet.
Refraction 2. Well, refraction 2. So anyway, in this refraction section, you can see every angle band starting from 90 going down to negative 30, all the way down to negative 30. You can see how the refraction changes. All right. Now, everything hath been concluded. We'll do open Q&A now. Now, against my better judgment, I'm unmuting you, Tony.
Okay, well, thanks for being a fuckwit about unmuting me. I always appreciate.
All right, that's enough for Tony.
Yeah, that's
Bye-bye,
enough.
Tony.
That's enough of you. All right. Does anyone have any questions?
That was hilarious.
Yeah, I have a question.
What's up?
What mechanism causes the stars to appear to move?
What mechanism causes them to appear to move? So are we talking like you think
Gravity.
that, well, no, they just move above us. I don't have a mechanism for it. Some people say that they're fixed to the firmament's spinning, etc. Couldn't tell you. We just observe them moving.
Don't you think that is a bit of a hole in your entire experiment when you're basing all these measurements off of something you have no idea about?
Not at all,
Jesus
because the current heliocentric dynamics are based off of GMM over R squared, where the mass cancels out and it reduces down to Kepler's laws, which is just pi over periodicity. Nobody actually knows why they move in relation to one another. It's not a problem for us.
I was only speaking about the stars appearing to move in relation to us.
No, I mean, well, that's to kind of show you the difference. Like, nobody knows. They just assert Earth rotate, or you could assume sky rotate, and they both produce the same thing.
Regardless of heliocentric or geocentric, it's still a globe. So I don't know why you brought up like helio math. But you were just elucidating how much of an explanation the other side does have when you have no idea what those stars are, why they appear to move, or anything about them, yet they're the linchpin in your entire argument and observation. It seems like a misstep.
Yeah, the stars move above us. If you want a causal mechanism as to how all that works, you're going to have to ask somebody else. All we know is that they move. And the reason I brought up the GMM over R squared for the relationship of solar system dynamics is we also see those same celestial bodies move in the sky. It's asserted that the causal mechanism is mass attracting mass, yet it just reduces to kinematics. So nobody actually knows why they move. And in terms of them rotating, like I said, you could say that the sky is rotating, or you could say that the earth is rotating. Both produce the same effect. Simply saying the earth rotates doesn't make it true, right? Especially when
No,
you're
but
using
the Earth rotating explains things like recession, right? Or the
Recession.
perihelions, sorry, like of Mercury, where they appear to recess across the sky. All of this is explained under the current solar system model with a spherical Earth orbiting around the sun. In fact, I just have to stress how little your side has in understanding of what these celestial objects are or
Yeah,
what
so
they
you just
are
observe and
doing.
declare, Reject.
And
hold on.
Observe
yeah,
and
it's a
declare.
working explanation.
One
It's
sec,
a
one
working
sec.
explanation. Rob, if you have an issue with any of astronomy, go out and research it and look at it yourself.
No, so I can
hold
observe
on.
and declare as well.
Yeah, that's Rob. You're not wrong, but please don't interrupt when the other guy is talking. But what I just stated about the GMM R squared relationship is that there are no dynamics as to why they actually move. It reduces back to kinematics. That's all anyone has ever had is kinematics, the observation of the motion itself. That's it.
Right, but the motion of these
Right,
stars and planets in our solar system and planets outside of our solar system is explainable by the movement of Earth around the sun and the rotation of Earth.
Are
That's
they
why we
equivalent,
are
David?
So listen, Rich, this isn't that hard to grasp, right? All the observations, number one, are done from Earth. They're all just a function of pi and periodicity. So what that means is if you see the sun go across the sky and when it returns to a year, if you apply that periodicity to the Earth instead of the sun, you could equally say that it's the Earth moving around the sun. Now, there's different ways that you could test that using a zenith mount filled with water, or you could build an interferometer to measure the absolute velocity. And when those were done, none of the measurements comported with the velocity of Earth having 30 kilometers a second. So,
well, the motion of the Earth can be relative, right?
Absolutely, it has to be relative to something, and it would be relative to the ether. And in that with that measurement, there would be a 30 kilometer a second relationship because
you're missing my entire point. You're missing my entire point.
No, Rich.
So continue to miss it, but
Rich,
go ahead.
You're missing my entire point because we just went over how the math is just kinematics and you could apply it to any frame. It's frame independent because it's asserted as relative motion. So what you're
but we're talking about a working model and an explanation when
man. So what you're asserting as mutual exclusivity isn't mutually exclusive. So there's no difference. So there's no actual contention there. And if that's all you have to say about the conversation, I'll let you get your final words off, and then we've pretty much wrapped up here for your questions for this particular one. If you have a different one, feel free. I'm going to unmute you now. Go ahead.
Well, obviously, they're not equivalent because the globe has a working model that explains the observable phenomena, whereas the flat Earth side just states the phenomena as brute fact and nothing more.
So on the globe model, what's the causal mechanism for the Earth rotating?
For the Earth rotating? That it has momentum?
That's not a mechanism.
The mechanism for the Earth moving? I'm not so certain.
But didn't you just assert that that's not?
Is it not good to have an answer? Yeah, you know what it is. But when we can look at the observable phenomena, when we look at an observable phenomena like stellar rotation, that is explainable under the globe model with the Earth rotating. It's perfectly reasonable. Whereas under the flat Earth side, stars move because stars move.
Stars move.
Aren't you just saying about that?
It's the.
Aren't you saying that about the Earth though?
Dude,
am I saying that about the Earth? No, I just said that I'm not sure. I'm not sure why it rotates. But
I'm not sure why the
my
sky
position,
rotates. I'm not sure why the sky rotates, bro. But the model
yeah,
itself is just based off of position and time, which is just kinematics, and that's not mutually exclusive to any model. This is why we need to use the occlusions to differentiate between model and reality, right?
the person who was trying to like throw it back on me by asking if I know how the Earth moves, at least I'm not saying I don't know what the Earth is, right?
What?
Anywho,
So when I ask how do the stars move, and you guys say we don't even know what stars are, to be analogous to what was asked of me, I would have had to say I don't know what the Earth is to say how the Earth moves.
well, the stars, not knowing what the stars was in relation to saying how they should angularly change or whatever. Now, what we're saying is that we both see the same thing on either model, right? We're both using the same ASCII grid to define positions of objects in the sky. We're saying that it's just a facet of our vision. You guys say it's a facet of the shape of the Earth. The only way that we could test this is by using star occlusions.
Wait, the stars move as based on our perception?
Nope.
I'm really
not what I
I
said.
understand you don't. You're really explaining that you don't have any idea what the stars are or how they're moving. So, thanks for elucidating that.
No problem.
Dude, you don't even know.
Glad I could help. All right. Are there any other questions or comments?
Real ones.
McToon's near. You got any questions, McToon?
How stars move isn't a real question. What's wrong with you guys?
Stars move on either model. We're trying to show something mutually exclusive. You specifically concentrate on something that's not. It's the same for both. So your point doesn't prove anything. Our point is mutually exclusive. Thanks to your participation.
Saying that it's included in your model because you observe it in reality.
All right. I honestly
Yeah,
can't anymore.
They can't
so-
imagine anything other than the coordinate system that was presented to them. Clearly, can't even grant it to you for a second because you can't imagine a coordinate system other than the one that they were originally presented.
Do you know what's
I got a
fascinating
question.
about that, Shalom, real quick, is that I was talking to someone earlier and they were like, but isn't everything heliocentric under the hood? I'm like, bro, every observation's made from an observer on Earth. How are you on the sun under the hood, but you're on Earth? But yeah, they literally can't conceptualize it being different. There's like a mental block there, even though the backbone of relativity theory is reciprocity between frames and even a general theory that applies to any frame to make them all equivalent. So super unfortunate to see that. But yeah, what was your question, Beast?
Oh, I was just seeing if anyone in here could actually steelman the celestial theodolite from the other side. That would be helpful. Maybe actually have some clarifying questions. Anyone on the globe side?
Is there anyone not clear what we're doing here and they would like to hear an explanation of it real quick just to understand it? Because I think if these measurements came back globe side, everyone on the globe would conclusively agree with it and immediately understand it, or at least pretend to. But because the measurements didn't come out globe, it's like a mysterious thing. It doesn't work, because of relative motion of the stars, yada yada,
Or your method is wrong.
Have you ever asked a globe person to make or validate your predictions, or you just make them in?
It's only been 34 weeks.
Yeah,
No,
Jesse.
no, I'm asking.
Jesse went out and used our method and made measurements. These are his specifically from.
But he's not allowed on anymore. So have you asked anybody? Has anybody else?
What does that have to do with him making the prediction successfully and doing it? If he's just because he's not allowed to talk here doesn't mean that he didn't do that.
Does he stand by those predictions? Or I'm just asking. I mean, it's not a.
Ask him. Ask him.
Okay. Has anybody else from the globe side agreed with your predictions for the globe Earth?
Everyone, because that's where Stellarium places the observer. So yeah, they all agree with how we're doing it.
You remember week 12?
They agreed with your calculations.
Yeah.
For what the globe would predict. Okay.
Mm-hmm.
All right. Thanks.
Till they
Yeah,
understood the implications, and then they pretended not to. That's what happened.
And if
Yeah.
anyone disagrees with the math, they are welcome to correct it. Actually, I think Embo once disagreed, and he gave me a different formula here. So if you look over here to this section, you'll see alternative derivations for the mountain elevations. For the old previous method was just doing some cosines with respect to the old central angle there. And then Embo hit us up with some actual spherical trig, gave us this. It comes out to 217, same thing. So they agree up to 9 decimal places. So every globe
good enough.
lad also agrees with us up to 9 decimal places, I would assume.
And what the other question I had is, what's causing the errors, the significant errors in your measurements for flat or globe?
Ooh, great question. So we actually share the same error, like the sum of these two differences is the amount of predicted drop over distance, and the error there produced by that is because the star isn't following 60 nautical miles per degree on its descent at 15 degrees per hour. It is following the 15 degrees per hour, but it is not following that descent rate. If it were, then these intersection times would, we would have had to wait for the 11 more seconds before it intersected. So for every single measurement, there's always, that discrepancy of it. And my interpretation of that is that the star's true position is not following that prescribed rate. And then when we go into the central angle stuff to verify how much the star dropped relative to the observer over that distance, which is also an angle, because angle equals distance for globe, based on how that works. So we note we take the difference in their true position at the peak and at their true position relative to the observer, and that angular drop amount is always the exact same arc length of the distance that it would travel. So it's like, you can think about it like, the star's time-wise is traversing 50 kilometers, and at the end of that 50 kilometers, there's a mountain peak that has a rise over run, to this elevation here, and that's when it's immediately gets occluded before it even drops to that using the 60 nautical mile per degree relationship. So
Well, why
the
don't
only
you why don't you factor that into your predictions?
why don't we factor how much it's going to, because we don't know how much the true position is going to be lingering like that. It's not something that we could readily predict. We would need
So
like more measurements to
couldn't
plot it out. Cause take
couldn't
a look at, so hold on a second. So take a look at this. So the celestial sphere predicts this blue line here, and then we don't know how much it's going to be lingering or how much it should be off or whatever, but we just have the data points of it being, of it not following that. So that's all we have right now for that.
so which ones? Okay, so those are the actual. Did you plot the errors from both the globe and the flat on this too, or no?
Both from the flat and the globe. So the globe would predict this right here, and then deviations from this blue line would be the error for both.
Okay, so where are flat Earth predictions on there?
Just where the there isn't one. It's just where the star was at the time of occlusion. So we don't
Why
have.
wouldn't it be interesting to put the flat Earth predictions on there?
Well, we don't know the angular deviation over as it gets closer to the horizon. The globe assumes that it should be that it should follow this blue line, but it doesn't. So we don't know.
So the flat Earth doesn't make a prediction for that particular.
For that particular thing, no, we do not. That's actually why we are studying the higher elevation occlusions, because like in this graph here, these angles are all low. We're trying to get angles that are like, 30, 40 degrees up in elevation so that we could see how it maps to the celestial sphere, so we can kind of get an idea of like the deviation or whatever. Now, of course, that would be like post calculated and all that, but I don't think there's enough data here to really.
So couldn't
solidify
another
anything.
interpretation of the errors that you guys are getting just be that the method isn't accurate right now?
If that were correct, then the central angles wouldn't line up. So no.
Okay, thanks.
Mm-hmm. Yep. That's why we say everything that we're doing here, can be verified also in Stellarium, because angle equals time. So all the relationships established, you can definitely confirm, where they should be with respect to the model making the prediction and go from that. So
Do you intend to publish this for scientific peer review or no?
I do.
Do you have a timeline for that or a hope, I guess?
I do not, but it is
Okay.
something that I aspire to do. I started a mini write up to be kind of like formal about it on the introduction here on the on the Obsidian, but I think it's like way too technical because I linked it to some globe lads, you know, and they were like, "What the hell is the two sphere model?" So I don't know if I need to like I don't know if I need to change or if they need to change, you know what I mean? So but I do plan on writing out something formally and sending it out to, you know, different universities, etc. for sure. I think it's one of the most significant ways to measure the shape of the Earth without just assuming the shape in the first place.
Yeah, dude, every term you use, just do a reference. That's all. On the bottom.
Yeah, that's what I started doing on this. I was like, you know, because it starts with cosmographia.
What the hell is cosmography?
Yeah, the P-Tall's book about the two sphere model and how they have to be the same to use them.
Oh, I see. Yeah, you did start doing it. Yeah, dude. You should
Yeah.
do that. That'd be awesome.
Yeah. So, but yeah. All right. Are there any other questions or comments?
Nope. Guess not.
How obnoxious was PhD Tony?
I'll self-publish it. Don't worry. I don't require, you know, it to be accepted or whatever.
What if I were to review it as your peer? Would that satisfy the requirement? Do you think?
Ooh, so here's what I'm thinking. We started a little coalition there, and if we all agree on something, it is henceforth the truth.
And then if we don't agree, we can discount it and never examine it. Is that how it works? Okay.
You guys aren't turning into Globers now, are you?
We might start a globe coalition and a secret society based upon keeping the secrets. It starts with a handshake, of course.
I mean, you guys have started to use math. You might eventually qualify as Globers.
How dare you? Well, dude, I'm starting to think some of the Globers aren't even qualifying as Globers.
Yeah.
Since we started using the math, only a couple of Globers have stepped forward to, you know, get a whiff of that math.
I mean,
Yeah, just
like
tell
those
just tell us where
standard-
just tell us where the stars go after they go to the horizon. Then
Out of
maybe we
your
can
field of vision.
Out of your field of vision. Very simple.
This
But
guy
in
is
other
so
people's
funny.
field of vision.
Listen, I don't have any math or understand what you're doing, but if I could just say the same 3 things I've been saying for 5 years, I'll get a kick out of it.
That's so
5
crazy.
years.
But
5 years.
my telescope says that the star's underneath me.
Yeah, right. How do you know the star's going beneath your feet? Or is that just assumed?
Hardy har.
Ha 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 ha.
Up on the other side of the horizon the next night. So
Yeah, it's weird. They just flop to the other side.
The other side of
right.
the horizon.
Maybe just like scooched around, like right below the edge of the horizon, then just like snuck around, like through the bushes, like a crawling sniper or something.
Right.
Yeah, like a crawling
Go down
sniper.
on one side, come up on the other side.
Alan, can I ask you a question? Like, of all the, like, if you had to summarize in your mind, like a ratio, like what percentage of all of the, even when you add like refraction with and without refraction, when you do all of it, if you had to summarize all of it as like, you know, is it 90% one way, 10% the other? Is it 95? Is it 80-20? You know, what, like in terms of like just all the results in terms of the shape of either planar or the sphere that they claim, like how would you say if you had to summarize it in one way, like how it breaks down or how close, you know, where the needle is?
So in terms of geometric to geometric, which is, you know, the cause of the occlusion, flat Earth 100%. For apparent positions, sometimes they match, sometimes they don't. And like by sometimes I mean like it'll be either above or below, which doesn't lead to an occlusion. It's not the cause of it. If it's above it, then it definitely didn't get occluded yet. And we see in the videos how the stars behave when they hit the peak. They don't really linger. They don't set into the peak as if they're going through an apparent image, like a refracted image or anything like that. They just, they start to vanish as they hit that peak. And that's pretty much, so that like kind of takes out the position of like, the refracted interactions and all that. And because of the refraction amounts mismatch on terms of being either above or below at the times, you wouldn't consistently be able to say like, the cause of the occlusion was this. So
Like for the side that where they claim the Earth is a sphere, like do they like how many do they have, and do they have any that are even close to actually giving the sphere result? Any that actually match it? Are there none that are even close?
sorry, I was replying to Tony. What was your question?
No, like in terms of showing a globe, like are there any that even indicate that are there any that have even like hit the actual globe result in any consistent way, or even gotten it at all?
No.
What it would be on a globe?
No.
Or just not even close?
No, only on the apparent intersections. Like for the ones we went over earlier, were like, I think it was Blue Mountain, or let me look here. Yeah, they ended up getting closer on the apparent intersections, but that conflicts with other measurements for different peaks. So it's like there's no consistency to it.
Have you done a standard deviation analysis on the results?
I have. It is over here in this section of the Obsidian. One second. So we did a RSS air analysis, which is just a standard Gauss distribution. You can find out more about that here. And then the air bars for globe and flat Earth based off of the occlusions are here. So, yes. And then in the spreadsheet
Alan, when you
here,
said Gaussian, aren't Gaussian planes like?
no, this is in
I thought
reference
they had to
to
be.
this is in reference to a statistical analysis. So basically,
Oh,
to sum up what
okay.
it does is it assumes like 65% or something like that of your measurements are going to hit like the worst min maxes, and then it averages that out for the air bars.
Oh, okay. So it's just it's a graph thing. Okay, never mind.
Yep. And then all of the information about that, also like everything that came from the RSS here, is on the spreadsheet in these sections here. Nope, that's air tolerance. Here we go. In the air tolerance section. So you can come here and see how we came to all of that. It was basically converting a Pi module into a Google Sheet, and then it just, take the data from the data table here, and then it output the necessary numbers to make the graphs.
And do you have the analysis that includes the globe with refraction, those numbers?
The analysis that includes the globe with refraction, we do not.
Okay, because that's, the actual globe predictions. So,
well, the actual globe prediction is actually made off of geometric intersections like eclipses and everything else, conjunctions, etc. So that's what we're using.
Great scientific retort. Great scientific retort.
Thank you. And then also when you're trying to, make a circle of equal altitude, do cell nav and all that, you're actually subtracting out refraction to use the true position. So if you would like to include that and do that on your own as a side project, that would be awesome. And then I'll implement it into the spreadsheet.
I've already
put graphs up.
Like, the funny thing is you did it. You just refused to acknowledge what the results are.
What do you mean?
Your own spreadsheet shows like the globe prediction, the white number, lightish blue, white numbers. We had this argument last month.
Where it's three arc
idealized load,
where it's 3 arc minutes over the peak at the time of occlusion, which doesn't lead to an occlusion. That's what if you want to do a thing off of a position where it didn't play out that way, that's great.
I'm looking at the time difference because you're measuring time difference. This all starts as time difference.
Mm-hmm.
So if we get a better time difference than you are, that means we're more accurate than you are. I know.
This time difference doesn't lead to the occlusion. If there was this much refraction and this was actually how much was there, this 19 arc minutes of refraction, then this star would have to go another 2 arc minutes before it gets occluded. It would still be above what you predict geometrically for the peak. If something's above the peak, it's not occluded by the peak, right? So you basing your position off of this is actually like, that's why it's not included. It means nothing. The occlusion didn't happen 17 seconds later. It happened at this time. So this amount of refraction isn't even tenable. Saying that it should be lifted up this much, because this is how much you need 1-to-1 in every scenario to explain celestial phenomenon. I mean, going back to the Novaya Zemlya effect, right? 10 degrees of refraction to explain that in the Arctic, 4 degrees of refraction to explain it in the Antarctic, over different latitudes. Hold on one second. Ranging from San Francisco to, I can't remember the place somewhere in Alberta, Canada. There's the amount of refraction needed to explain it is the exact amount. So this is like an untenable hypothetical that never happened. But if you were like, want to use that as your position, dude,
the
I
number
don't
that's
care.
almost twice as high in green is tenable and happened is your claim. So 2 minutes 21 seconds is untenable, but 3 minutes 52 seconds is just okay.
No, the star didn't. No, the star didn't even get occluded when we predicted, because it's not following the 60 nautical mile per degree relationship. It occluded at this time. It occluded earlier than that. We would need we would need 27 more seconds, and we would only.
Both the predictions have errors, but our error is smaller than yours.
Your error is smaller. Okay. Listen, guy. Listen. That's a great take. When we get into the central angle relative to how much the star had to move or drop relative to that observer, it's the exact amount of distance angularly between the peak and the observer. So there's no the offset isn't created by refraction or what have you, because if it was, then the central angle distance would be affected by that, and there's never a mismatch in that. So if what you're saying was true about this refraction amount, what would happen is the occlusion would happen 17 seconds later, and there would be a mismatch between the central angle relative to the observer and the positions of the stars at the time of occlusion. There would be a different value, and they never are. So your position
what happens,
isn't tenable.
Like, use the same argument. Like, if the numbers were switched around, is that what you'd be saying, or would you be saying 17 is less than 27? We're right.
If the numbers were switched around, I'd be a glober, dog.
He'd be a glober, yeah.
So if the globe numbers were worse, you would be a glober.
If you understood,
if the globe numbers were less accurate than the flat numbers, you would become a glober.
If the geometric intersections at the time of occlusion or emergence were closer to what the globe predicts, then the Earth would be a globe definitively.
They are closer. That's what your spreadsheet says. That's the part that kills me. Your own sheet. I didn't do a bit of this work. It's all yours. You say the globe's more accurate, and you don't believe your own numbers. It's hilarious.
Listen, dog. We're talking about geometric intersections. You're talking about an apparent position that didn't follow the amount of actual refraction 1-to-1 as prescribed to explain every other phenomenon if there was no mountain there. So I could give a fuck about this number. This is super irrelevant to me. You're holding on to this for dear life because that's all there is. These numbers don't reflect what the globe actually predicts. It's closer to what flat Earth predicts. And
I agree. The pink numbers aren't what the globe predicts. Like the pink numbers are bad. That's a great straw man, but that's not what any of us are predicting. So the fact the pink numbers are bad, no surprise. We agree.
Listen.
Okay, what numbers are you
hold
predicting?
on.
What?
Hold on a second. For geometric intersections, these numbers are not bad for the globe. What I meant when I was saying they don't reflect the globe, I mean they don't reflect it in terms of like it gives evidence for the globe. Now, this is exactly, shut up for a second. This is exactly what the globe predicts because they're basing it off the observer. You can go into Stellarium, enter these times, and get where the star's true position is relative to the observer. So a geometric alignment for let's go back to Pikes Peak. So the geometric alignment for this at 217 is exactly observer-based predicted, and this is the intersection difference between them, okay? You make eclipse predictions, conjunction predictions, all celestial phenomenon aligning is based off of true geometric intersections, not the apparent positions, number one. Now, the significance, yes, and the significance of that is because an apparent intersection doesn't cause an occlusion, number one. This is why Mike became a flat earther, because when he went over these intersections, they should be reversed if the Earth is a globe. The full arc length should never be traversed relative to the observer, because the only thing at the end of that is a mountain peak with a rise over run. Before that, there was a chance that it could have been a peak with rise over run minus globe drop, but that didn't happen. So the important fact of this is these geometric intersections and this arc length, and the full arc length relative to the observer and the peak, because that same arc length is also what defines the star's drop over time. You may speak now.
So, I mean, there just isn't a lot to say that I haven't already said. Like, the number in pink is a straw man. Like, yes, I acknowledge that's what the geometry without refraction would be, but you can't just ignore refraction. That's the core mistake you're making with your whole process is you pretend that using an occlusion means you can ignore refraction. It doesn't. You can't. Once you include refraction, you got to use the numbers in white, which are the more accurate ones than yours.
Oh, wait, can I ask a question, Alan? Check this out.
Yeah, one second.
Well, how much does this? Okay.
Listen, if your refraction hypothesis mattered, there would be a central angle difference. There never is. So we must do this and do untenable. Go ahead.
Okay. Maybe I missed, like, I haven't watched all your presentations, so it's possible I've missed this. But when you say essential angle difference, what do you mean by that?
What I mean by that is that the observer is, some arc length away from a star, from the mountain peak, right? Now, at the time of emergence or occlusion, we reference that arc length. Okay. We subtract the position of the peak, of the star at the peak from the position at the observer. That total difference is the arc length between the peak and the observer. So what that means is the star was able to traverse that distance of the arc length, and then it immediately got occluded. Okay, if the Earth were a globe, it couldn't have traversed the full arc length. It would get occluded earlier because the globe predicts that the star is moving at 60 nautical miles per degree, 15 degrees per hour. So it already it intersects with 217 before it does with 230 relative to the observer.
So is this just a restatement of the whole, like, it's off by an arc minute or 2 arc minutes or whatever, like you were saying earlier?
No.
Is that based to the same thing?
No.
Okay. Maybe I am misunderstanding you.
So basically,
so I may run it in a minute.
No worries.
Yeah, but go ahead.
What was your question, B? Sorry, I had to. Felt like
No, it's all good. He made a claim. He said you guys are ignoring refraction. Like, we need to take refraction into consideration, even with the collusions. My question to you is, how much is a star refracting when you can't see it?
That's a question to me. I mean, whether you can see it or not doesn't change the path of the light. It just changes whether the path of the light intersects your eye. So it's doing what it does in the atmosphere, whether there's a mountain in the way or not. It's just
so how much refraction needs to be added in if you can't see the star anymore?
I mean, what you do the physics, you figure out what the path of the light would be, and that tells you the answer. And I mean, this is why I pointed his sheet so much, is he's done the math. That last number is the prediction with refraction for when it would be occluded. So.
Oh, okay.
So it gets occluded before the full amount of refraction gets used. This isn't a straw man of your guys' position. It's showing you that there's not that much refraction. That's not a tenable position to use for a metric for anything. Once the occlusion, if this were true, then the distance would be different for the central angle when you subtract these two from one another relative to the distance to the observer and peak. But it never is. It's always exactly as soon as it hits that arc length, it's done. Every time.
Might have to think on that a bit.
All right. Like, think about
I'm pretty sure you're wrong, but I'm not sure I can put a finger on why well enough to make a real argument out of it.
That's fair. So think about it kind of like this, right? If the Earth is a sphere, right, we're taking this little arc length section of 27 arc minutes between us and the mountain peak, but the complementary angle to that is 80. What was that? Would that be like 89.33 or something like that?
Something?
Yeah. So it would be like 89.33. So if you multiply that out with nautical miles, it completes a 360 degrees. So only in that small section between observer and peak, where there's two possibilities, one is rise over run to the peak, the other one's rise over run minus globe drop, the exact amount of drop, relative to the observer is that arc length before it gets immediately occluded. And if there was refraction differences, then it would linger, then the apparent position would linger on, and it would create a mismatch between the arc length and the difference at the time of occlusion.
Okay. Would it not also be the case that the 11 seconds the other way would also be a central angle problem then?
11 seconds the other way.
Like the green number. If that was, would that not also create the same problem of the central angle issue?
The apparent position would be what, 245? I see what he's saying, Alan. You see what he's saying?
For the apparent positions, yes,
Right.
but I think for the would it be for the true positions to fully traverse that, it would also change it. It would also create a difference in the central angle. I'll work on making a thing to like simulate that out so we can see the differences.
It's a good point. I'll say yes, actually.
Because it should,
okay. Yeah. Because basically my take on this is all experiments have error. Like the fact that your numbers are 11 seconds off or whatever the number might be, that by itself is not a huge problem. You want to analyze and understand the error. But like the fact there is some error is inevitable. You're not using atomic clocks. You're not using like theodolites. You're not like, you're limited by reality.
For sure.
And the fact that you're not doing this on a massive research grant either.
Limited by reality. I like it.
There's going to be some error. But we'd want to understand like what the error is and why. And if you just say that your prediction has error, our prediction is good, like you got to at least analyze the error of both sides using the same approach. That's more or less what I'm coming from.
Oh, I absolutely do. That's how I ended up finding out that the relationship between our error difference and the globe's difference for the intersections is the sum of that is the half central angle. What they would predict as drop over distance for the earlier occlusion to create the central angle mismatch. So like, in other words, instead of being 27 arc minutes for us for that full traverse, the globe should occlude around like 15-ish arc minutes traversed. It shouldn't be the full 27. But yeah, I will work on making that more clear. I started it kind of down here a little bit, but I'll dress it up. Right. So that is a pivotal part to understand. It's a good question.
Fair enough.
If there's more,
so have a good one.
Yep.
I have a question. If there's more, I'm looking at the Shane's graph there, the little GIF. If there's more refraction from the peak to the celestial body, would that strengthen or weaken your case against the globe model?
If there was more refraction from which position?
The peak of Pikes Peak to the celestial body. Right now, the star. It looks like from the graph, I don't know if this is probably just because it's graphics. It looks like it's kind of the same arc of this of the light bending down to the peak and onward, but in reality, it should be a lot more after the peak. Would that help or hurt your case? Well,
if there were actual refraction conditions affecting it, like I was just discussing with Auludius or AlanSpaceAudits, there would be central angle differences. So I don't think that it actually matters because when the true position intersects, it seems to immediately cause the occlusion.
Cause the occlusion. Well, it's a combination of both angles of deviation, or all the angles of deviation from the viewer to the peak to all the way to the star as well. Well, through the atmosphere.
Right. You would expect the changing of it, but that doesn't seem to be the case. But what that would do is it would, delay the occlusion, and it would make the refracted position intersect with the true position. It would make these numbers a lot more closer to what would be kind of what I would consider a tenable position if you were going to say that the true position was occluded by the geometric position of the mountain peak. These numbers would have to be like, in the arc second range rather than, multiple arc minutes above, because we can definitely measure arc minutes above something, like the occlusion wise. So if they're up in the arc minute range, I would say that the hypothesis is untenable, because it's, if it's above it, it obviously couldn't be occluded by it. But yeah, if there was like actual conditions affecting it like that, then these numbers would be lower and more closer to what the globe, for that to predict, instead of being over it or under it in some cases. Like North Peak is devastating.
Can I ask Xander?
I've got one more question.
Yeah, I'll be right back.
Go ahead.
Yeah, you might have covered it, but do you have any observations in the southern hemisphere? I asked you this before, and you said you were looking into it.
Oh no, we don't have any southern hemi yet. And if you're in the southern hemi and you want to make, what's the bounty at? Is it 300? I don't want to say 300 if
Did
it's
you put
not.
300 already?
I might have. Let me double check.
I think it's 200 last time I heard it.
Let's see. Celestial bounty, 200 per qualifying. So we'll do, if you're in the south and you can get a measurement that is over 128 kilometers, we'll do $300. If you're sub 128 kilometers, we'll do 200. So to lay out a couple of things here, you can find out more about that on this website here. And we need a couple of things, right? We need your latitude and longitude. We need the lat and long of the peak that you're looking at, or at least its name. You can find that out from websites like Peak Finder, etc. And for the best occlusions, right, if you just get one star occluding the mountain, that's not super helpful. What we need is like a series of stars, at least like 2 or 3. And if you can get occlusions where there's multiple stars on screen, that'll help us identify the stars later, because sometimes it can be really hard to identify them. So if you're shooting at night and you don't know the exact, azimuth that you're looking for the peak and whatnot, then your occlusion is going to have some additional stars in it so that we could reference it. If you're lined up with the peak exactly, etc., and your ASI, then a single, a couple stars or whatever shouldn't be an issue, because we can line up the azimuths. But yeah.
What does your model say in terms of what would you expect from a southern hemisphere prediction? Would it be different?
So the differences here for the star's position, true position, not following the 60 nautical mile per degree. 1 second, maybe I could show you exactly. Did I close it out? Oh no. Okay, so in the north we have like this amount of deviation here. I suspect that it will be a greater deviation in the south. I suspect that the intersection differences will be off by more.
What are you basing that on?
Just that the south would be bigger, would be larger. But the coordinate system is made off of symmetry, like forced symmetry to the true positions. So the coordinate system wise, it's symmetrical, but I think in reality, the south is bigger.
And historically, the south was always harder to map.
Yeah, it would be awesome to get that data. So getting like the long distance on it would tell us the most extreme deviation to it, like the North Peak measurement here. We would see just how far it's deviating from the celestial sphere. But
where do you get the rise over run on your graph?
Rise over run comes from the mountain elevation and the difference between observer elevation and mountain elevation at sea level. Oh, I'm sorry. That's for the elevation. For the distance, for the run, that's just the distance. So we take the arc length from that. So we take the latitude and longitude and do Haversine to get the distance.
The Haversine is a globe formula, right?
It uses.
I know that you've been asked that before.
Yeah, no problem. Yeah, so Haversine's a calculator, and it requires a radius value for it to be useful to. Like the whole model is based upon that. So to calculate distances between that, you have to use the radius. Yes. But my position is that it's, you know, a coordinate system calculation. It doesn't have to do with the position of the actual ground. It has to do with positions of where the stars were, because that's what defines latitude and longitude. So the coordinate system is spherical, therefore requiring a spherical calculator to compute distances on it. You could also take the chord of these distances, and it comes out to be, I think for Pikes Peak, there's like a 14 centimeter difference. So like at these distances, the difference between a great circle and a chord is, you know, negligible.
I appreciate it.
Yep. I prefer the celestial, or I prefer using the Haversine though, because it's basically with the radius of, you know, 6,371,000. That's the, you know, the celestial sphere that they use for the backbone of everything. So it just kind of makes it nice and uniform. Is what we were getting into. You know, Mike and Jesse were using different websites to compute the distances, and they would like change by a little bit, and it was dependent on which website you were using and which model you were using to compare it to, because there's like a polar radius thing where they add like 20 kilometers to the North Pole, and then like 20 kilometers to the South Pole or whatever. So there's like a plus or minus there for, you know, anyway, there's like, long story short, they're like getting different distances and comparing and all that and stuff. So I just centralized it to, you know, whatever the lat long was and the great circle is close enough for me.
So why don't you use the Pythagorean theorem?
The Pythagorean theorem is rise over run. So like this is all fucking.
But like in terms of making your calculations, like a squared plus b squared, you should be able to like calculate the angle. And
well, for the central angle stuff for the globe, we use the 2D Euclidean projection, which where the sides add up to 180 degrees, using, you know, the side A, side B, lowercase a and b, and all that for the angles and stuff. And then rise over run is literally just you know, that is verifiable by the Pythagorean theorem. So not quite sure.
Well, for the run, like, can you use the Pythagorean theorem for the run?
You can use it for anything on this spreadsheet. I don't really understand your question. This is all based off of triangles adding up to 90 degrees or 180 degrees. So it's all Pythagorean.
Is your spreadsheet available to like a read-only version, or
so
you might have posted it already? I just got to the conversation.
Yeah, so
right, cool. I'll take a look at it.
What you'll have to do is make a copy of it, because of the drop-down menu. It doesn't allow users to edit it. But yeah, you can make a copy of it and you're good to go.
Appreciate that. Yeah, I'll take a look at it. Thank you.
Yeah, rise over run's just a 90 degree triangle.
Yeah, I got you. I'm gonna look into it before I ask my question.
Yep, no worries. All right, lads. It's been about 2 hours. Thank you all for your time. If there are any further questions for closing or whatever, we can do like maybe one or two more. But if everything's pretty much wrapped up, we will go ahead and close for the night. We'll be back next week, hopefully with the data, or at least some of the data implemented from the new observations here. And
I just wish flat earthers used math.
Well, you know what they say. You can make spaghetti using tomatoes or using ketchup. If you use ketchup, it doesn't taste quite as good. All right, lads. I'll be back. I'm gonna mute while I do the outro. But the presentation thus has concluded. Oh, and Tony, I saw you were asking some questions during the thing. I missed most of them, but if you would like answers to them, if you send me a DM, I'll DM you now so you can have it in your history. But if you send me a DM of your questions and comments, I will answer them. I saw some of them were worth answering, so I will definitely.
Well, it's not for my benefit so much as your own. So I noticed that you're asking for GPS coordinates. you should let your observers know what accuracy you require for your results to be meaningful. You're not requiring GPS altitudes, which means that you are using some form of digital elevation model. It would be useful for you to know which digital elevation model you're using and what the errors are associated with that. Whether or not your rotation, whether or not stellarium includes oblateness and variations in oblateness, whether or not your calculations include rotation. You keep on using 15 degrees per hour. That's the wrong number. Only slightly wrong, but it is still the wrong number. And it varies through time. Length of
varies
day
for latitude
calculation.
as well. But yeah, we actually do have that in there.
And of course, celestial latitude of points on Earth's surface varies through time as well.
Yep.
So you're not there yet, but you're getting into the point where you need to do these things with sufficient precision that they can be ruled out as potential contributions. And I'll echo what Alcidius said before, or Alcidius, however you pronounce it. Claiming that refraction can be neglected for this is not a safe assumption. And I don't think, and your attempts to make the argument, I found extremely difficult to follow. And I have a degree in mathematics. So you're not making, you seem to think that your case is watertight mathematically. To me, it still seems a bit garbled. And when you're comparing two models, globe and flat Earth, you need to fully describe both models. And it feels to me like the flat Earth model is not fully described. There are portions of it that you have not yet explained to me certainly I feel that you haven't explained in sufficient detail why star trails should be circular if the Earth is flat. If the Earth is flat, the geometry should dictate, and your arguments about the psychology of vision don't carry any weight because we get the same results when we use cameras. So all of this stuff about the non-Euclideanness of human perception and human visual interpretation, that's a red herring. We get exactly the same results, or pretty much the same results, when we use cameras as when we use the naked eye. So that is not an argument for why you get these effects. And so I would encourage you to sit down and work through your model from the ground up, because the fact that star trails and celestial object trails are circular is a major problem for you. You can say it's just the same as the globe. Well, it shouldn't be if the Earth were flat. If the Earth were flat, you shouldn't be seeing this. And you just saying, well, it happens, so obviously that's how things work. Well, yes, I would argue that's a good reason to not think that the Earth is planar. And you need to, so you're starting from the point of view that the Earth is planar. Okay, that's a great starting point. I start plenty of my arguments from that exact assumption. Now let's work through the consequence of that. How, if the Earth is planar, do star trails show up as circular for everyone?
Okay.
And
yeah, sure.
we don't need to discuss that now. Yeah. But it feels like a question you need to be able to answer.
Well, I would like to add a couple of things because some of them are already accounted for in there. So the latitude dependent variance and positions of the stars using 15 degrees per hour plus or minus the Lati variance. You can verify any position here that's calculated. There's a time interval associated with it. You can go into Stellarium and check the true position or apparent position, whatever the calculation time is for, and confirm that the star is at that angle into Stellarium. In other words, the spreadsheet matches Stellarium, and any timing and angle relationships are described, within that. We've compensated for that as much as we could.
That doesn't answer my question.
Well, it answers some of it to start with, and then
all right,
yeah, no, it doesn't. Stellarium uses a radius of 6,371,000. Otherwise, we couldn't make the same angle predictions. So they use the idealized celestial sphere and that's what we're using as well. And then in terms of elevation differences for the data and whatnot, we're using the GNS overlay on Google Earth, and then you can see what they've mapped out for elevations, and then compare that to what the elevations are said on Google Earth, and those tend to agree with each other pretty good. And then there's also a website called peakfinder.com. If you go there, I'm pretty sure they're referencing something similar to what Google Earth is referencing, because their numbers very strongly
That's
agree
horrible.
with those elevations as well. Oh, is it?
Yes.
Well, listen. Hold on
Google-
one second before we get to that, because I'm about to dip. If that's horrible and it doesn't work, please provide me with the correct elevations and where I can get them, and then we'll go from there. But just saying it's horrible is low key retarded, because it's the fucking GNS, dude. Like, it's a different number now. Like, come on.
Before you run though, IC Spin did say he asked if you had time for just one more quick question, right? IC Spin.
I got you, Spin.
Yeah. Just quickly, if you're able to calculate the elevation angle to a peak, let's just say Pikes Peak, for instance, and you know what the measured peak height elevation is, then couldn't you just calculate what your run should be based on the Pythagorean theorem and doing a simple trigonometry calculation to calculate what you would expect
if you
the
already
distance
had,
to be, and compare that to the globe?
if you already had the angle, you could.
Well, you can measure the angle though from your location, right? And then you can look at, what it should be predicted on a flat Earth, say the Gleason map or something similar, where it has the continents laid out according to what a flat Earth might predict, and then base the distances on whether or not it matches flat or globe, right? And then you could simply reverse engineer like what kind of shape you're on would be my.
Not really. And then, because like at these distances, the difference between an arc length and a chord is only 14 centimeters. So like for Pikes Peak, for example, 50,000 meters, that's 50 kilometers. The difference is only 14 centimeters. So reverse engineering what it should be versus what it is or whatever is,
So the reason that Google Earth is bad to use for elevations is because the elevations in Google Earth are given relative to local sea level. And local sea level is assumed to be 0, but local sea level varies the height of that relative to the implicit datum. And so if you're using 2 points and they each have different local sea levels, you've got the difference in elevation between them is not the same. And sea level can vary globally by plus or minus 100 meters. So using Google Earth in order to calculate elevations is not a valid way of doing it, and certainly it's not something that you should be doing if you have any pretense to surveying expertise.
Right. So check this out, big dog. Not only do we use Google Earth, we also use the GNS overlay, which shows the topographical elevation for those locations. We compare that. We also compare it with what Peak Finder says, and also when you go to Wikipedia and look at the names of the peaks, they have the elevations published. All the elevations agree with one another. So if you're saying that's not good enough or whatever, then you'll have to show me where there's an actual difference at. Because if you go to our spreadsheet and you look at the mountain elevations that we have and you go to try and confirm your own mountain elevations, I think you're going to find that there's not much of a difference.
What about the observer altitude? Right, so you've got the altitude for the peak fine. You've got the yes, Alcidius, that's the geoid spheroidal difference. Okay. Over 128 kilometers, it probably isn't that large in most areas. But for instance, if you're working along the Indian coast, 100 kilometers is enough to introduce a few meters. But the other point that I would argue here is so you know the peak height with with you claim great accuracy. I still think that if you're using Google altitude there, you're wrong.
Did
But
you
it's
hear
the
me, dog?
The observer height.
Jesus
The observer height also features into this as a problem, right?
No.
Well, if the observer height is wrong, but the peak is right, then your whole model is based off of shit that's not correct. But I can overlay the GNS map over it and get the same things. And my friend Eric also is super, he's a globe lad. He's super into GPS stuff. He was verifying the orthometric height, using all of that and the differences. There's everything's spot on. There's nothing wrong with this. Now you can keep hypothesizing your scenario, or you could pick one of these from the spreadsheet and show me where the elevations are incorrect. Until you do
I
that,
think that's what he should do.
until you do that, then you really don't have an actual argument. And I appreciate your contentions because those are valid, but they're already taken for, and it's as accurate as we can get down to GPS orthometric transformations, apparently.
All I'm doing is pointing out potential points of imprecision. I'm not necessarily claiming that these effects are large, as Alcides is pointing out. They may not be. All I am doing is pointing out potential points of imprecision in your current formulation. And if you're not prepared, and okay, you're not prepared to do the work to make it more accurate,
I've already
I'm
done
not going
it.
to do it for you.
Buddy.
That's fine. You've had them.
1 second, dog. You're not going to reframe that to you haven't done the work to make it accurate. Did you not fucking hear me compare it to 3 different sources and an additional orthometric GPS height from a person who believes in the globe? You're either not hearing me and you just want to repeat what you're saying, but that's a non-point, and I don't need to be here for that. So I'm going to go ahead and dip, and then you can just talk about it while I'm not here. That would be preferable to me.
Said you almost got it, kid. You almost.
Jesus. Ugh.